Hello, everybody. Good afternoon. My name is Kevin Liang, and today I'm going to talk to you about performance tuning Apache Solr for dense vectors. So first off, to make sure that everyone is in the correct room, who is this talk for? Well, first and foremost, if you are currently using or plan to use dense vectors in Apache Solr, it's a great place to start. If you are working with a large data set, perhaps in excess of 100 million plus documents, perhaps you work on an application that has strict latency requirements, or your system is hitting latency as a bottleneck, or simply that you want to reduce your compute resource usage costs. If one or more of these apply to you, then that's fantastic. If none of these apply to you and you're just curious, that's also fantastic. Obviously, we're going to talk today about dense vectors, but more specifically, we're also going to talk about running and configuring a search index. Specifically, this idea here that performance isn't free, that the more effort you put into tuning your search index, the better performance you're going to get out of it. Now, we're not going to be talking too much today about model tuning and relevancy. There are going to be plenty of other talks at the conference that hit on those topics. We're going to be more on the infrastructure side of things. So before we jump into the content, just a quick side about where I come from and who I am. So I work for a company called Bloomberg. Bloomberg is a tech company that is a leading provider of financial data, news, and analytics. Its main product is the Bloomberg Terminal, which is used across the world by top traders, bankers, and financial institutions to power their everyday decision-making. And of course, as part of supporting that mission, search and information retrieval is of paramount importance. Serving the right data to the right people at the right time is key. So I work on the search infrastructure team. Our product is Apache Solr as a managed service internally to the engineers at Bloomberg. And it provides a variety of functionality, including but not limited to automated provisioning, deployment, automated backups, security, alarming, monitoring, et cetera, et cetera. We deploy over 1,000 Solr clouds on our on-prem data centers on self-managed hardware. And this in turn powers over 1 billion document updates daily and over 4,000 queries per second across our clouds. If you have any interest in those infrastructure topics, I encourage you to please come talk to me or any of my team members who are also here within the conference. After the talk, we'll be around. So today we're going to talk specifically about the use case of one specific tenant that we have. They use Apache Solr to power. This is a specific application in the Bloomberg Terminal that people use for financial document research. So financial documents meaning things like disclosures, things like analysis, things like that. I know this UX is very, very busy, but rest assured, at the heart of it is a search experience that is probably very familiar to many of you. There's very common keyword search experience. You have your search bar where you can input your query. You have some filters. You have some other functionality like synonyms and entity recognition and some sourcing and things like that. So like any sort of traditional search solution, it comes with its benefits, but also comes with its limitations as well. So for example, if users are providing very vague queries, you might get a lot of noise. If they're providing very specific keywords, they might be excluding documents. They might be over-filtering and excluding documents. But overall, users aren't really looking for documents. They're looking for answers to their queries. They're looking for answers. So last year, this application team comes to us and starts the conversation about how can we improve our search experience? We've been hearing a lot about these ChatGPT-like solutions. Can we train our own LLM? What about this new technique we've been hearing called RAG, et cetera, et cetera? But the buzzwords aside, no pun intended, I swear. The vision is to build something that is more akin to this, where we have a much more clear solution where the user can provide a natural language-based query, and they can interact intuitively as they would like to a human being. And in turn, they get a synthesized answer returned that is built on context and data, transparent attribution to the source data. And is this context serving that we are primarily going to focus on today. And of course, this is powered by, you guessed it, dense vectors. So So at the time when they came to us with this project, we had some Solr 9s running. As you may know, dense vector was introduced with Solr 9, but we hadn't really done dense vectors at scale. And so, of course, the first thing we need to do is build a proof of concept, understand what it is capable of. So the application team goes and trains a BERT encoder model to produce vectors of size 1024. As a proof of concept, we take a smaller subset of that data. So we take about 2 years of most recent data and we apply paragraph chunking. This yields a data set of about 169 million documents. This is quite an interesting number because if you go online, there are lots of benchmarks for various vector solutions. However, a lot of them tend to focus on data sets in the range of 1 million to 10 million documents. So this is in a little bit of a different scale. So we provision them with a Solr cloud, and we set them up with some pretty standard setup for us. So it's a 6-way T-log poll replication in cloud mode. We put them on hardware for 10 CPU cores, 1.2 terabytes of RAM, and 10 gigabytes of heap. And then we set up a schema for dense vector field definition using cosine similarity. And so when we ingest all that data and put it into Solr, this is the Solr admin UI for those who are unfamiliar. This is built into Solr. A lot of numbers on the screen. So apart from the top level of the 169 million documents, it's also maybe interesting to note the segment count. Segments are the subfiles that make up the Lucene index underlying Solr. And then also the index footprint on disk, which is 1.8 terabytes, which is not small. And so we take this Solr cloud setup, and of course we need to go and test it, see how it does. So we run some benchmarks with queries. Our k is 50, meaning return us the 50 closest vectors to our target query. And we get a distribution of latencies that looks something like this. Now, the first thing that may jump out at you is the latency is quite high. I mean, maybe it's not the worst, but compared to our standard BM25 text offerings, it is quite a bit slower. And as well, you can see that it degrades as we increase the throughput. In fact, the throughput tends to cap out at around 50 to 55 queries per second. Once we pass that 50 queries per second, the P99 goes from almost 1 second to quickly becoming multi-second, and it quickly becomes untenable. But more so for this application team, it just does not meet the customer needs. The application requirements are just, it needs to be faster. So this graph kind of underlies maybe what the root problem sort of is. For this chart, for 100% indicates 1 CPU core all the way up to the 10 CPU cores that we have. And you can see that we're very concentrated up in that upper range. There's a limited granularity to this data because it's sampled, but even within the data points, many times it will hit up to that container limit, and we end up with lots of CPU throttling. So we are maxing out the CPU on the machine. So as an intelligent and highly motivated engineer, this is a clear opportunity to come up with a creative and well-tailored solution. This is a very standard design pattern. But jokes aside, sometimes the simplest, most head-on approach, it can be useful. And so we took the largest machine in our inventory, which had about 60 CPU cores, and we put this cloud on this machine and dedicated it entirely. And what were the results of doing this? So, well, we saw the end-to-end time from our initial about 900 milliseconds to 1 second. It dropped about 10%, so there's some improvement. We saw the queue time also drop a bit, but I think it's very clear to people in the room that giving it 6 times the resources did not yield 6 times the realized performance. This is obviously not an effective solution. So we tried vertical scaling. How about horizontal scaling, which in the case of Solr, this comes in the form of sharding. So we take this cloud and we shard it 12 ways. So we split subdivide the collection into 12. And our theory was that this would allow us to parallelize some of the operations. We would see more thread utilization by the Solr process, which we did see. And we did see some improvement in overall throughput. So we saw maybe 5 to 10 queries per second more overall throughput. But for latency, for the speed at which the requests come back, we didn't see many significant gains. So again, not very successful here. So we took this approach from the hardware perspective of trying to make it faster via more hardware resources. So what if we attack the problem from a different angle? So rather than making it a beefier system, what if we reduce the work that needs to be done by the system? So how can we reduce the computation required? So we initially chose cosine similarity function because it's kind of standard. It's easy to understand. It's the angle difference between the two vectors. However, this is expensive to compute. If you look at the mathematical definition, you can sort of see why. Like especially when you have many dimensions, 1,000 dimensions, you're doing many multiplications, and you do the square root through the divisor of the calculating the magnitude. So, but what if for that lower portion, what if we were able to normalize it, and then if they were all unit vectors of length 1, then the bottom part drops out, and we don't have to calculate it. But moreover, it becomes equivalent to the dot product, i.e. that we don't lose any relevancy, but we are able to calculate it through a much simpler computation. So the solution here is to take our vectors, normalize them at ingestion time, and then use the dot product. Fairly simple. So what were the results of doing this? So we saw, first off, we saw a significant reduction in CPU usage. So before we were hovering around that 10 core to 11 core range, and we saw it come down to an average of about 4 cores of CPU usage. And then for the end-to-end time, we saw more reduction from our initial 900 milliseconds down to about 700 milliseconds. And we saw the queue time as well significantly drop down. Can we further improve on the solution? So before we were talking about calculating distance between vectors, but what about the index itself? What about the segments? So as we know, Solr KNN uses HNSW, or hierarchical navigable small world graph-based structure for their indexes, and it looks like something on the right where you have multiple layers and it gets more dense as you traverse further down the layers. And this data structure is quite good at finding vectors. It's in logarithmic time, i.e. when you subdivide into the layers. However, each of those segment files that I mentioned earlier has its own disparate graph. And so what you see is that even though it's very quick to find vectors within one of these indexes, the overhead of joining results between the searchers can be very expensive. This is more akin to linear time. So you can kind of infer that the more segments I have, the more latency I will incur. So the solution here, what if we change our merge policy to more aggressively merge down these segments into fewer segments, consolidating my index? It is worth noting, though, that as with everything in engineering, this comes with trade-offs. So by having larger segments, you're going to probably incur some costs when it comes to indexing time, replication, and potentially recovery. So please note that if you do choose to go down this road. So here we have, in our configuration, our merge policy. Don't worry, the specifically interesting parts of it are, first off, the max merged segment MB, i.e. the maximum size that we allow Solr to have for its segment. We bumped this from originally 5 gigabytes up to 15 gigabytes. And the maximum segments per tier, we reduced this, thus forcing more segments up into that upper range of being larger. And you can see on the bottom that we initially started with almost 500 segments, and we've now reduced it more than half down to about 200 segments. So implementing this merge policy, we saw that our CPU usage continues to go down. We go down from 4 cores to about 3 cores. We saw our end-to-end time drop down to reduce by about a third from our initial, and then the queue time dropped down by about 2/3 from our initial. I'll let this slide speak for itself. So can we make it even faster? So many of our Solr clouds are running Java 11. Please have some recognition for the courage to come up here and publicly admit that. Some of you may have sat in on Uwe's talk earlier today, and which he was talking about Java 21. So one of the incentives to upgrade to Java 21 is that there is a project called Project Panama. And what it's doing is it's providing more efficient direct foreign function calls directly through the JVM. replacing the JNI, i.e. that you no longer have to go through an abstraction layer through a separate library to do many of these operating system level functions. And specifically within there, there is a vector module, which has many functions that are optimized for vector calculations. And you can, in fact, utilize this in Solr through a JVM argument. You can enable it for Solr. So enabling this, we saw our lowest usage of CPU for our system yet. We're now able to bring the usage down to below 2 cores even of usage. So far, we focused a lot on CPU, but what about the other half of the equation of our system, which is what about memory? Well, if you don't properly optimize your memory, you may see something like this. What is this? Well, this is a graph of major page faults, i.e. when the operating system is unable to find the page in memory and has to go to disk, and loading it from disk is very slow and very expensive. So the way we tackle this is obviously you want to reduce your index size and have as much of it fit in memory as possible. But so first off, it's worth noting that with vectors, there's certainly a significant storage cost. So for 1,000 dimensions, and each is a 4-byte float, 4 kilobytes per vector, approximately 169 million documents. The minimum footprint is 600, 700 gigabytes. So it's quite substantial, especially compared to some text fields. And as with many search indexes, it's ideal to fit the entire index into memory for reasons such as disk reads, obviously slow, prefer memory, and then loading pages also uses CPU cycles. There can be thrashing. In addition, as we mentioned before, we wanted to reduce the number of segments we have. If we have a smaller index, then we can also have fewer segments as those are consolidated. And then also worth noting, this is a smaller thing, but network transfer as well. So for k equals 50, the response size is about 700 to 800 kilobytes. Not the most, but transferring it for high throughput, like high traffic, you're going to have some cost over the network as well. So the solution here is actually quite a simple one, which is you can make vector fields indexed but not stored, i.e. don't store a raw copy of the vectors, and you can therefore reduce your index size quite a lot. So so we started from, this was our index snapshot, where we have 470 segments and 1.8 terabytes. With the merge policy, we were able to reduce the number of segments that we have by more than half. And now, by making the vector fields non-stored, we're able to take that footprint of 1.7 terabytes and bring it down to about 800 gigabytes. And then you can also see here that the segments have also decreased as well. So we are making it much, much slimmer, much more efficient. So what are our final results once we've combined all the techniques that we have mentioned above? So for k is 50 and 50 QPS, we saw the end-to-end time drop by almost 90%, able to bring it down from closer to 1 second down to closer to 100 milliseconds. We were able to take the queue time down by over 2/3, from 300 milliseconds down to below 100 milliseconds. And the average CPU usage, we were able to bring from about 11 cores of average usage to about 2 cores of average usage. And with reducing the amount of computation required, we're also able to push the system harder. So whereas before we were capped at around 50 queries per second, we're now able to push the maximum throughput at over 200 queries per second, which is a significant increase. So if you are running Solr and you want to use dense vectors, what are some things that you can do to hit the ground running and avoid some of these pitfalls? So first is reduce your CPU operations where it's not necessary. So pre-normalize, use dot product similarity. In fact, this is advocated on the Solr ref guide now, I believe, as well. Use an aggressive merge policy within reason based on your indexing requirements. Use Java 21, Project Panama vector module. And then for memory management, reduce the index size, use non-stored vector fields where possible. And that's it. Thank you so much. Any questions?
Thank you. Question, did you also consider quantization as a performance technique in order to get latency down?
Yes, so that's a fantastic question. So we have considered it. So with quantization, not every technique used here is going to have zero effect on the retrieval and the recall. However, most of these techniques have minimal. With quantization, there is a bigger question mark of how it's going to affect the relevancy return. So we're still in the process of testing that. However, I will also say that the quantization solutions in Solr There have been changes pushed to Lucene that have not come upstream to Solr yet, and we're in the process of also building those into later Solr versions. So a combination of internally at our company, we are still testing, and the other is to build better native support for quantization into Solr itself. Yeah. Yes.
Okay, unfortunately, we don't have any more time, but it's always good for networking if you go to the speaker afterwards and talk to him. I also always do this as well, so you don't need small talk in the end. Yeah, thank you very much. Give another round of applause, please.
Thank you.